Up until now, we've been comparing our formulas for our ideal and our actual mechanical advantage. Now, they are not exactly the same. In fact, there's a very important difference between the two. But for now, to keep things simple, let's assume that our ideal and our actual mechanical advantage are the same. So let's assume our IMA is equal to our AMA. And let's give this formula a name, this IMA equals AMA formula. Let's call it the ideal effort force equation. And hopefully by the end of this video, it'll be incredibly clear why we call it the ideal effort force. And actually, let me widen that out a little bit. But why we call it the ideal effort force equation. And there is a good reason. But for now, I think it's good enough if we just know that the ideal effort force is the name of the equation. And of course, if we say that our IMA is equal to our AMA, then we can say that our DE over DR is equal to our FR divided by our FE, or I like to call it our Deers are free equation. And it's important to note that this is no different than IMA equals AMA. These are the exact same formula. This is just a different way to write the ideal effort force equation. In other words, this is just a second version of this equation. But let's go ahead and give this formula a try. Let's draw ourselves out an inclined plane here real quick. And let's add a height here. And let's say we have some box that we want to push up this incline. And let's say it weighs, I don't know, let's say it weighs 60 pounds. And that's the weight going straight down. That is not the effort force. Let's say we don't know the effort force. But let's say we do know the length and the height. Let's say the height is 5 feet and the length is 30 feet. So our distance effort is 30 feet and our height or our distance resistance is 5 feet. And the question becomes, what is our effort force? And so let's go ahead and figure that out. And to figure this out, we're going to use this ideal effort force equation. More specifically, we're going to use the Deers are free version of our ideal effort force equation. So let's go ahead and rewrite that equation. We'll say DE over DR is equal to our FR over our FE. And so let's plug those numbers in. We know our DR is 30 feet. We know our DE is 5 feet, so we just plug those in here. 30 feet goes on top, divided by our distance resistance, which is 5 feet. And we'll set that equal to our FR divided by our FE. And the FR is clearly 60 pounds. That's the weight of the object we're trying to lift. And we'll divide that by its effort force, which we don't know. That's kind of the whole point here. And then to solve for our effort force, all we have to do is cross multiply and divide. We cross multiply the two numbers that are across from each other, that's 5 feet and 60 pounds, and then we'll divide by the 30 feet, which is across from our effort force. And so we'll just plug in those numbers. We'll put 60 pounds on top multiplied by 5 feet. And we'll divide that by 30 feet, which is across from our effort force. So we'll put 30 feet on bottom, and we'll set that equal to our effort force, or our FE. So to figure this out, we'll plug this into our handy-dandy calculator. And I'm going to hit the numerator over denominator button to make this sort of fraction kind of equation. And I'm going to plug in my numbers. I'm going to say 60 multiplied by 5 on top. And then I'm just going to put 30 on bottom. And this will solve for us. We hit enter. And what do we get? We get 10. And so we'll say our effort force is equal to 10 pounds. And I know it's pounds because it's a force. But another way you could figure it out is you could say, okay, feet over feet cancels and we're left with just pounds. And so the effort force we would need in this system would just be 10 pounds. But in reality, it could not actually be 10 pounds. It might be something like 15 pounds, because in the real world, we have to deal with things like friction. And other things too, but let's just say friction to keep it simple. 10 pounds would be our ideal effort force in a perfect world without friction. And that's the only way we can actually say that our AMA is equal to our IMA. And for that matter, it's the only way you can say that our DE over DR is equal to our FR over FE, or as I call it, the Deers are free equation, which is just a fun way to remember the equation. But what I'm saying is the only way these can be equal is if we had some ideal effort force equation, which is where the name comes from. But think about it. Adding friction won't change the distances here. If we add friction to the system, whether we're in a perfect world or a non-perfect world, these distances will stay the same. And for that matter, the friction won't change the weight or our force resistance. The only thing that will change if we added friction to the system is the applied effort force. So the only way the actual and the ideal mechanical advantages can be the same, or equal, is if we assume we have some ideal effort force. And later on, we'll talk about how to calculate an actual effort force and what the difference is between the AMA and the IMA and how to figure all that stuff out in our efficiency lessons. But for now, let's keep assuming that our AMA is equal to our IMA. Let's keep assuming that we're doing math in some perfect world. Therefore, our ideal effort force equation is true. And let's go ahead and try to solve for another problem. And so let's go ahead and draw ourselves another inclined plane here. Let's give it a height and let's add some ramp, some incline. And actually, I think I'm going to move this down just a little bit. But let's say this time we have a 75 pounds box or crate. Doesn't really matter, just some weight here. And let's say this time the length of the incline is 40 feet. And let's say the height, let's say we don't know the height. Let's change it up a little bit this time. Let's say this time we don't know the height of our incline. We don't know the distance resistance, but we do know the length of the incline. So hold on. We do know this length here. Let me add the arrows here. And let's say we have some ideal effort force required to push this weight up this incline. And let's keep it simple. Let's say it's only 15 pounds. What would be our distance resistance? And so we'll say distance resistance equals question mark. And so to figure this out, we'll just use the exact same equation. We'll say dE over dr is equal to our FR over our FE, which is just our d's are free equation, or more specifically, our d's are free version of our ideal effort force equation. And so let's just plug in our numbers and figure it out from there. And so what do we know? We know our distance effort is 40 feet, and we know distance effort goes on top. So we'll put 40 feet on top, and we'll divide that by our distance resistance, which we don't know. And so we'll just leave that as a variable. And let's just set that equal to our FR divided by our FE, and we know those two numbers. We know the force resistance is just the weight of the object that we're trying to push up, which is just 75 pounds. And so we'll put that number on top for our force resistance, and we'll divide that by our effort force, which we said was just 15 pounds. And then to solve, all we have to do is, again, cross multiply and divide. And so what do we know? Okay, what numbers are across from each other? Well, 40 and 15 are across from each other, and 75 is across from the variable. So that's the number we put on bottom. That's the number we divide by. And on top, we'll put 15 pounds multiplied by 40 feet. And to solve this, all we have to do is pull out our handy-dandy calculator. And we could hit this button again, but actually I want to show you how to do it just in case you don't have this button on your calculator. All I'm going to do is say 15 times 40. I mean, it's just a simple equation, right? We just say 15 times 40, and then we take that number, 600, and divide it by 75. So we just say divided by 75, and we get 8. And so what does that 8 mean? Well, we actually forgot to write down what this is equal to. This is equal to our variable that we're looking for in this equation. When we cross multiply and divide using these two proportion problems, we set them equal to the variable. In this case, that's dr. And that dr is just 8. And what 8 what? Well, it's a distance, so we know it's feet. But if you're not sure, you can always look back at your equation and see that pounds cancels out. And so the only unit we're left with is feet. And so the question is what does it mean to get a distance resistance of 8 feet? Well, what it means is, in order to make this incline have the mechanical advantage it would take to turn a 75-pound weight into 15 pounds, we would need the incline to be 8 feet tall. We would need that to be our distance resistance in order to make this system true in an ideal world.